Welcome back. In this lecture, we want to talk about horizontal lifts of planar curves. This will allow us to construct many horizontal curves in the Heisenberg group H1. An important recall that I have to make is that at a given point P, we can write any vector in both coordinate systems, the standard ijk, and also the coordinate system given by horizontal vectors and the complementary one t. And the coefficients correspond very nicely. Indeed, the partial x, partial y components exactly correspond to the x and y coordinate components on the other system. And the third component is exactly calculated in terms of the others. This shows that a V belongs to the horizontal space at P. That means it's in the span of x and y, if and only if this last component is 0. And from that, an important other fact follows, and that is if you write any horizontal vector in the standard ijk coordinates, that is the partial x, partial y, partial t coordinates, if it is horizontal, then C is uniquely determined in terms of A and B, depending on the coordinates of the base point P. Because being horizontal means this quantity is 0, and C is exactly solved in terms of values of the point P and the coefficients A and B. Let us introduce the curves by the functions giving their first coordinate, second, and third coordinates. So let this be differentiable at some tau. Then gamma prime at tau belongs to the horizontal space at gamma t of H1, the condition we use for horizontality of curves. This holds if and only if, well, we just write that condition I gave above with ABC and XYTs. So when you translate it here, because the point P is gamma t and the vector also is in terms of derivatives of gamma t, we end up having a combination of derivatives and the original values. So this is true if and only if the third derivative equals twice the derivative of x multiplied y minus x times derivative of y. Had it not been for the minus, this would be as if product rule applied to x times y, but there's the minus one. So let's give this important condition star. So at one point, being in the horizontal span is equivalent to this condition. So corollary will be that an absolutely continuous curve gamma from some interval into R3 is horizontal if and only if star holds at almost every tau in A, B. Because by definition, being a horizontal curve means it is AC plus the horizontality condition holds, which we just saw is equivalent to the star. And it is required to hold almost everywhere, not at every single point. Okay, so what this tells us, there are a few remarkable things about this. This shows us, the star shows us that the third component of a horizontal vector, this t, is completely determined by the first two. So here you only have x and y on the right-hand side, and the derivative of t is given by that, so by integrating you recover t. This is, of course, not at all true for an arbitrary curve in R3, which can even go vertically up, where right-hand side will just be 0. And here is where being horizontal plays the big role. And this shouldn't be really surprising, because for horizontal vectors, as here, knowing A and B determines C, because this condition is equal to 0 for horizontality, and C can be recovered from A and B given that point T. So it's really following immediately from this observation. Okay, but the most useful aspect of this is that it will help us build and construct horizontal curves. Okay, and I want to put it in the form of a theorem. So how do we construct horizontal curves in H1? We start with a curve in R2. So suppose gamma bar defined in a compact interval into the plane is absolutely continuous. And write its coordinates as x and y. So gamma of tau, let's write as x tau and y tau. Of course, x and y, the coordinates are functions of tau, so we can call them x and y. Then the claim is that we can define a new function t tau by integrating from a to tau the quantity 2 times x prime of s ys minus x of s y prime of s. Of course, it's the one from above, from condition star ds. Then this one defines, the claim is that this defines an absolutely continuous function and the curve gamma constructed as x tau and y tau, which we started with, and then augmented with this t tau. Now this is a curve into R3, and the second part of this theorem is that this is a horizontal curve in H1. So that's the theorem. If you start with an absolutely continuous function in R2, you can construct an absolutely continuous curve satisfying the horizontality condition. The last part of this is that gamma bar that we started with is orthogonal projection of this other gamma, which is the reason why the remark is that because of last condition, gamma is called the horizontal lift of gamma bar. Okay. So let's look at the proof, and I include this especially because I want to show you where the condition, the assumption of absolute continuity, which we have been using the whole time, where it really plays a role. So we start by the observation that because gamma bar is assumed to be absolutely continuous, the function 2 times x prime of s ys minus x of s y prime of s is integrable. Hence, this integral formula t tau, because it's integrating that function, is well defined. Also, for later use, when you define a function by an integral, this has been featured many times in this channel, we can take derivative, and derivative of t at tau will be the value of the integral inside. So absolute continuous functions are basically the functions where fundamental theorem of calculus in both of its forms holds, that derivative of an integral is the integrand, and that integrating derivative gives us the change in the antiderivative. So AC is the class of functions where what we knew in Calculus 1 in undergrad does actually hold. And the counterexamples cannot exist in AC class. So anyway, because we're integrating an integrable function to define t, when you take derivative, you go back to the function itself. So this becomes 2 times x prime of tau y tau minus x tau y prime of tau at almost every tau. So now we have the condition that x of tau, y of tau, and t of tau are all absolutely continuous functions. So gamma, defined as above, is absolutely continuous. So we have checked the first condition of being a horizontal curve, and that is being AC. And moreover, let's call this double star. By double star, which holds almost everywhere, gamma is horizontal. Because horizontality condition, remember from the previous fact, is equivalent to star, right? If and only if star holds, and condition double star is just saying that the star does hold. Maybe condition double star is just the star. Okay, and clearly the last part of the claim of the theorem is that pi composed with gamma is just gamma bar, because you just look at x and y.